examples. What does it do? Okay, ready? What are enzymes? Or what do you know about enzymes? May I just open this to the floor? Anything you already know, just give it a quick shout and we'll just do a word splash on the whiteboard. Enzymes. Okay, before your body. What about proteins?
Digestion.
They are made of proteins, okay? Made of proteins. Okay, I hear the word catalyst. Anything else? Okay, Jackson, what did you say just now? You say
Digestion.
okay, for digestion. Lock and key model. Okay, for those that done the SLS, or did we do this in JSU? Okay. Okay, anything else? Well, where did you learn that from? Okay, so Ishan said enzyme, substrate, complex. Wow, oh, big one. Anything else? Okay, there's a portion where you can bind to. Okay, maybe I'll just say binding site. For what? Sorry, binding site for? Okay, so the enzyme must somehow bind to the thing it's going to break, right? Okay, so there's a binding site. Okay, so we see a word splash on the whiteboard. Currently know that enzymes can be found in your body. They're also made up of proteins. Yes, they are made up of proteins. So my advice to you is that for this particular chapter, study it with proteins because enzymes are proteins. Okay. Next, some of you mentioned that enzymes are involved in digestion. Okay, that is half of the story. In reality, you will learn that enzymes are also involved in building things up. Okay, not just for breaking things down. Okay, we learned that I think in JH2 we learned about a lot of enzymes. Actually, where do we find all those enzymes? In your digestive system, right? Okay, so now we open our mind a bit more. Enzymes aren't just found in your digestive system. There are some on your eyeballs, breaking down foreign particles that land on your eyes. There are enzymes running through your blood vessels in your blood to destroy or break down things or to build up things. There are enzymes in your tissues to help you build new parts. Enzymes are involved in breaking down and building things up. And they are not just found in your digestive system. Okay, so I think it's a misconception when we just show you that side of the story in JSU. You know what does the word catalyst mean? Okay, so enzymes help, one of their fundamental roles is to help speed up any chemical reaction. So while we often say that enzymes help to digest or help to build things up, actually, a little bit more accurate would be to say they help speed up these reactions. In reality, left to the elements, the environmental forces, things will break down naturally. Enzymes help to speed things up. Okay. These vocab, lock and key, enzyme substrate complex, we'll look at them in a while. Alright? So, with this broad overview in mind, today we're going to start a new topic, enzymes. We are going to move a little bit away from our biomolecules, but always keep in mind the topic of proteins, because enzymes are made up of proteins. Okay? Okay, so may I get you to open your class activity? And the can of play. Perfect timing. Okay, now get you to open up the class activity, you'll find a QR code. Can I get you to access this QR code? You'll find a model, a digital model of an enzyme that you are familiar with, that we've seen before too. Yeah, our favorite enzyme. Next week we'll be going to the lab and we will make use of this enzyme to digest things. Okay, so let's get familiar with this enzyme. Once you're in the model, may I invite you to go through the first few steps, A all the way to F. Okay, may I get you to go from A to F. You know that you are done with this task if on the next page you attach an image. Okay, where is the image? Oh, this is not a teacher's copy. You attach an image here to show that you completed task up to step F. May I invite you to do A to F now? The purpose of this is to help me see how much you understand from your SLS for those that did it. Okay, for those that didn't, today is a session for us all to catch up. Okay, some time for you now to complete A to F. Free to talk to each other, yeah? if you have time, you can move on to the next part of the class activity, which is to identify the levels of structure present in this enzyme. Okay, we just practice this skill as much as possible. Can describe the protein structure in bullet points this time. Just meant to get you to exercise that skill. last minute or less. How many teachers use this? Okay, get ready to wrap up. Oh yeah. 10 is just nice. Okay, let's have a look at this particular enzyme. Perhaps let's go straight to the structure first before we dive into the vocabulary of enzymes. Number one, what are the levels of structure present in this protein? Stand up, all three, right? At this point, are you able to describe the various levels of structure? For the primary, some vocab you could use is that primary structure consists of the specific number, type, and sequence of amino acids. The secondary structure consists of either alpha helixes or beta beta sheets, and they are held together by hydrogen bonds. The tertiary structure is a 3D globular structure, highly folded, held together by 1, 2, 3, 4 kinds of bonds or interactions. Yes? Yeah. So I think last round when we saw this particular model, Christine also asked if there's a difference between the purple and the pink, is it? Is that a question? Personally, I'm not too sure if there are different kinds of alpha helixes. But for you, if you were to see a swirl like that, you would classify it just generally as an alpha helix. But I suspect, based on the way it's color coded, there may be different ways in which the alpha helix can go. Maybe it's a directionality thing. Okay, so 3 levels of structure. Today, we're going to look at one more layer. If a protein is an enzyme, it will have one more feature. Okay, what I can do now is I can show the molecular surface. When I show the molecular surface, I'm trying to show, if I look at it from a surface point of view, you can see that this particular protein has a lot of contours. There are like valleys and then there are like mountains here and there, right? It's not a nice view. You also find that if you were to click show glucose dimer, okay, this is the thing that the enzyme will break down, okay? And if you try to search for that particular glucose dimer, it is somewhere over here. It is embedded within a cleft of the enzyme. I'm going to stop rotation. What do I mean by cleft? You see this indentation over here? Yeah? There's an indentation and this molecule is binding to that cleft, that belly of the enzyme. Okay? Earlier on, Zoe mentioned binding site. There's a name for such a binding site where the molecule will bind to. We refer to that binding site as the active site, because this is where the reaction will take place. Okay, the active site. So I'm going to introduce all the vocabulary you need to understand this topic. Number 2, we refer to this is the enzyme. Okay. What do we call that molecule that binds to the active site? We have a name to refer to it. We refer to it as a substrate. Okay. Next, when a substrate binds to the active site of the enzyme, okay, so see how I use it in a sentence. Say again. When the substrate binds to the active site of the enzyme, we will form what we call an enzyme substrate complex. Okay, an enzyme dash substrate complex. Usually in biology, if you see the word complex, it means that there are a few things joined together. enzyme substrate complex. Okay, so some vocabulary for this chapter. Anything else? You can also find a similar diagram in your notes. Some of you have progressed to the notes. Okay, and you will see something very similar. You could just add on there, or you can add on in your CA. After all, they're all part and parcel of the same collection of the revision material. So as a biologist, I hope you can appreciate that if someone were to draw this Pac-Man-like structure, appreciate that we are really simplifying this. We are just drawing the molecular surface of that protein. It's really a simplification. Okay. And that's why I think students don't often associate this with proteins. Because our idea of proteins is that they have folds here and there. But there are many ways to draw a protein. This is one of the easiest way to draw. Just look at it from a surface point of view. Yeah? Right. So, for an enzyme to work, a few things must happen. Number one, the enzyme and the substrate must first collide with each other. Right? If they don't collide with each other, there's no chance the reaction will occur. And I say collide because at the end of the day, enzymes don't have eyes. They are blind. This is whether a reaction happens or not is by chance of whether the enzyme and the substrate bump into each other. Okay, they are blind. They are not sentient, these enzymes. Sometimes we get a misconception that enzymes are small little living things that will go around looking for things to chomp on and break down. No, they are just proteins floating around, and when the chance comes and it collides into a substrate, the reaction will occur or be sped up. Number two, other than it colliding, we need something very important. The shape of the substrate must be complementary to the shape of the active site. So it's not enough to just bump up. You need to have chemistry. Yeah? So let's say I have another substrate. By chance, this round line also bumps into it. But no chemistry. Nothing is really going to happen. Okay? Last but not least, other than bumping into each other, okay, this is for us, for our class. So this is FYI. Bonds need to also form, at least temporarily, so that we can hold the substrate there long enough for that reaction to occur. Okay, so the last point is FYI. Bonds / interactions.
Are they temporary?
Yeah, they are
So
temporary.
what kind of bonds and interactions are they?
From my knowledge, they are non-covalent ones. Yeah. Non-covalent meaning like
Metallic.
hydrogen, ionic, such bonds. Yeah. Yes.
Is it the bond that attracted?
Sorry? Or is it these bonds that help to break the substrate? Okay, it really depends. Every enzyme has its own way of speeding up the reaction. Sometimes it applies tension to the substrate, causing it easier to break. And sometimes we're not even breaking it, sometimes we're building things up. And it's about holding it in the right place for the best orientation. Okay? So these are not permanent bonds or interactions, they are temporary. Just meant to hold it there. Okay? FYI. In most cases, we'll describe up to this point that it needs to collide and the shape of the substrate needs to be complementary to the shape of the active site. And use the word complementary rather than same. The active site is like a valley. You cannot say that the shape of the valley is the same shape as the substrate. Yes?
If you're saying that the third one must happen for it to carry out its function, does it mean that there are cases where the substrate will come into active site and no bonds will occur?
Yeah, so if a substrate somehow manages to fit in there, but the correct interactions don't occur, then it will not hold it long enough for the reaction to occur.
But why will the correct interactions not occur?
Because it could be, depending on the amino acids here, the R groups, it could be the R groups are not ideal for whatever functional groups on the surface of the substrate to hold it there. Yeah, the substrate also has, every biomolecule has its own functional groups. So the idea is about whether the functional groups match up the correct areas to hold it there long enough.
So it's about the R chains not being in the correct order.
The primary structure, right? So you see how important the primary structure of protein is? It actually determines how useful or how specific the active site is going to be for the reaction. And which actually is a very nice juncture to say that, therefore, enzymes are specific in action. They will carry out, very often in biology, you will find that enzymes carry out or catalyze only one reaction. If you study a little bit more, you'll find some instances when some enzymes can catalyze more than one reaction. But most enzymes catalyze only one reaction. Because it takes a lot of factors for it to actually happen. Number one, must first collide. Number two, the shape of the substrate needs to be complementary. Then the last one, the interactions and bonds need to be the correct ones too. So it's not that easy, and therefore it's very specific in its action. The new vocab here probably will be the idea of complementary. Okay? And enzymes being specific in its action. Okay, so we have a few new vocabulary for today. With that in mind, if we look at this particular enzyme and this particular substrate, there are two theories of how substrates bind to their enzymes. One of the theory is called for those that have done the SLS, it's called the lock and key model of enzyme action. Okay, lock and key. If I look at this as a lock and key, if I look at the enzyme and the substrate as a lock and key, which one is the lock, which one is the key? Okay, right? Okay, often we say we describe the enzyme as a lock and the substrate as a key. The model of the lock and key describes that the substrate shape is complementary to the shape of the active site. Okay, this is the one that most of us know of. Over the years, we found that actually when we look at a lot of enzymes shape and the substrate shape, even though the enzyme can catalyze the reaction, we find that the shape of the active site is not exactly complementary to the shape of the substrate. So scientists propose a second theory of how enzymes will work. The second theory is this. Perhaps the substrate is complementary, but not exactly complementary. The theory goes like this. After the substrate binds, the enzyme will change its shape. The enzyme will change its shape to fit the substrate, to make it exactly complementary. So this is the second theory of how enzymes work, and we call this theory the Induced Fit Model. In both cases, the substrate needs to be complementary in shape to the active site. But in this particular model, the active site shape is not exactly complementary. It can still change its shape a little bit more to make it exactly complementary. Chinese, sorry.
So are you saying in that induced fit model, does that mean that there could be different types of enzymes that digest one single substrate?
Oh, because it would seem like I want substrate, different enzymes come in and then they induce fit the
Exactly.
substrate. Okay, so it's still very specific action. Because remember, that's why I brought in the third one just for our class. Bonds and interactions are still really important. Okay, so let's say it can induce fit to be very complementary, but the correct R groups are not present to form these interactions, then we still cannot. So it's still very specific in its action.
Then which is the correct model?
Which is the correct model? Both models actually exist. Sorry, not both models exist. There are many different enzymes. Some of them follow the model on top, some of them follow the model below. Is it required of you to know which enzyme can follows which model? Not required of you. Okay, we just want to expose you to two different models. Yes, it's enough.
The bonds are more important than the shape.
Oh,
The induced fit kind of fit the shape.
right, okay. So now it seems as though the bond interaction is more important than this. But let's perhaps look at the lock and key model. Right? Let's say I have a substrate that is square shaped. Right? It cannot even fit into the active site. We won't also expect the bonds and interactions to be aligned just nice for it to occur. Right? So I would say both are important. I brought in this third one for our class because I just suspect you will start probing a little bit more. What is this? Oh my god. I was like, what is it crawling my teeth? Okay, it's not. It's a male end. Fly free. Oh, it's a queen end. Okay, so two models of enzyme action. One is the lock and key, one is the induced fit. Which one exists? Actually, both models, different enzymes adopt, I wouldn't say adopt. We find that there are enzymes that follow this model and some that follow this model. Some, their active site are really nicely complementary. Some of them, not fully complementary yet, but can induce fit. Personally, I think, okay, even though the data is not out there, I would think that this model is, you'll find more enzymes adopting this particular model. Because I think it's very hard for a substrate to be exactly, complementary in shape. So I think this model is, I think in the real world, this model is likely the one that a lot of enzymes have. Is it just me or is it quite humid in this case? Yes, I see.
The thing only uses the active site, I don't know why the rest of it.
What thing? The substrate?
Yeah, the enzyme.
The enzyme only?
Only the active site is used. They don't know the rest of it.
Oh, okay. Oh, okay. Only the active site seems to be the useful part. Everything else seems to be not so useful, right? Okay, so think of it this way. In order for this particular active site to be, the shape to be formed, you require all the other parts to form in the correct way also. So the other parts are useful in a sense just so that we can just achieve this three-dimensional active site shape. It's useful to that extent. So we have a problem. If I were to denature an enzyme, we lose its active site too. Yeah? So if I were to heat up an enzyme to very high temperatures, this active protein will unfold, the active site will disappear. No longer functional. Yes?
Then what if you just copy the amino acids that are in the active site?
Yeah.
And then you just use that, then you wouldn't do anything to the substrate.
Yeah, I'm not sure. But if you copy just this region, so you are saying maybe just create a smaller thing like over here. Okay. Technically, if you could keep the amino acids just nice in that configuration, I guess it may work. I'm not sure. I'm not sure if anyone has done that before.
Would it affect the bonds and interactions between the enzyme and the substrate? Because in the tertiary structure, then the amino acids will already be bonded to other amino acids within the protein itself. Then
Yeah.
will
Okay, so are you saying, right, actually if we create a smaller version, we may expose some R groups that cause some other interaction to take place. That's fair. Actually, then that's fair. So it's almost like in the grand scheme of things, they have to work together. Everybody has to work together just to achieve this small region. Look at this amylase, the active site is actually really small. Right? We really fold this whole structure just for that small little clef. Shanice, were you raising your hand?
Yeah. I want to ask you the part about you said about how if you denature it, the active site will disappear, so the enzyme is no longer functional. So then will the enzyme become a substrate?
Why does the enzyme become a substrate?
So because it needs to get digested, right?
Oh, I mean, for you to consider a substrate would imply that there is another enzyme that could digest it. Right?
Oh, so it could and could not be a substrate.
I guess so. Yeah. If I had another enzyme that could digest this protein, then yeah, it is now a substrate.
Okay, and one more is the Induced Fit Model, right?
Yeah.
So if it's too big, it can like become smaller, so it fits in like your thing. What if
Yeah.
it's like too small? Can it like enlarge to fit?
Actually, from my observation, most of the times the enzyme are larger than the substrate itself. Yeah. But you look at this one, in fact, whatever I draw here is really obscenely off scale. You look at such an enzyme, and then you look at the substrate. Actually, the region where it's going to catalyze the reaction, right, it's not often very big. Yeah. Okay. Any more questions? Yes.
Since there are enzymes that break down proteins, then is it possible for an enzyme to break down another enzyme like just like that without?
And yeah, so there are enzymes that can break down enzymes. So actually, that's the body's way of sometimes to stop enzymes from working. Because after all, right, you cannot possibly suddenly heat up yourself to stop a particular enzyme from working. So our body does have certain stop measures. It produces another enzyme to digest the top enzyme. Yeah. So enzymes are really, really powerful biological catalysts. They can do a lot of things. Okay, so that's the vocabulary. And if we go to the next class activity, okay, for those that are a bit sleepy, I know the temperature is not really ideal. Drink some water, it will help you out. Sometimes when you're dehydrated enough, your brain not hydrated at such sugar, your eyeballs will roll behind. Okay, if you're done, you can scroll down to look at these two images. A student brought this particular nut cracker to class before. I've seen this before. First, I asked students to demonstrate the models of enzyme activity. Then one student brought this to class in 1 year. She brought this tool. This tool's function is to crack open a melon seed to eat. And then she told the class that she's using this to represent one particular model. Okay, to you can discuss among yourselves, which model do you think she's trying to represent? And are there limitations to the model she's trying to represent? Okay, using this tool. Okay, have a quick discussion. Okay. So we asked, does the active site need to be like the same size as the substrate? Because here I almost imply that, you see, it almost nicely parks of it, right? No, it doesn't have to be the same size. It could be that I've seen also substrates that are smaller, much smaller than the active site also. Something look something like that, you know. So it need not be the same size.
Can it be bigger also then? Like it juts out of the thing.
Yeah, could be. So remember, number one, it needs to have at least some parts of it that's complementary in shape. It also needs to have the correct bonds and interactions. Okay, that was interesting. Yeah. Oh, okay. Can you ask, can multiple substrates fit into one active site at the same time? Why do you ask that question? Okay, if the substrate can be smaller than the active site, then Taiwan's next guess is that, then technically you can fit more inside, right? It's true. For enzymes that need to build things up, technically you will need more than one substrate inside, right? So let's say I want to make something that is consists of two parts. So the substrate, I could have two substrates binding to the active site. Once they bind inside, then the reaction occurs to create the bonds, and then voila, oh my, voila, I create a new product. Okay, so yes, more than one substrate can bind to the active site. Yes.
I thought enzyme digests the substrate, right?
Enzymes are okay. So it's a misconception, I think, created by us. Because in GH2, when we say the word enzyme, we say that it's used to digest food, right? Enzymes are used to do more than that. They don't just digest things. They don't just break things down. They can build things up. Everything that is built in your body, from the proteins to the lipids to the nucleic acids, all of them require enzymes. So even to build your DNA from nucleotides, an enzyme comes in to build it. To build your proteins from amino acids, in a very chicken and egg way, there is an enzyme to also help to build a protein. Yes?
The Induced model, the molecule that is like in the active site is glucose, but then shouldn't the substrate be like amylose or amylobacterium?
You're right. Okay, so the model that's provided, I understand amylase is supposed to digest starch, right? But so that we don't lose focus of the enzyme, they provided just two parts of the starch. Yeah, they just provided two of the glucose of the starch because the enzyme will only bind to two glucose of a starch at any one time to digest.
So is it like the substrate or is it considered the product? Because like when amylase digests starch, it does its own molecules.
Right, okay. So is it so is it a before or after? Okay, then actually in this case it may be an after scenario. The molecule is going to be about to be shipped out. Zoe? Wow. Okay, let me search through my brain. Yeah, I do not recall in my time studying biology an enzyme that's two active sites. But I know of an enzyme that can catalyze two different reactions. But does it mean it has two active sites or is it the same active site? I don't know if it's the different or same one. Okay. Well, that's a question I need to ask myself. An enzyme have two active sites. Okay. Okay. Yes.
Must the substrate like bond together to make one substrate before it can be
Rejected.
before it can be fit into the active site?
Oh, okay. So Zoe is asking if we follow what Tanya was asking, right? The two substrates before they enter, does it need to first bond together first, then fit it? Don't need. Okay, so let me show you maybe an image. Enzyme substrate. Enzyme substrate. Okay, let's type enzyme substrate. So maybe something like that? Or something like that? Yeah? So we have two different substrates binding to the active site, then the reaction occurs. Okay? Unfortunately, the active site I've drawn here is a very, very, very simplified active site. Sometimes you may see enzymes like that, then the active site goes something like that. A dip here, and then another here, and then like that. But we consider this entire thing as an active site. Okay? Yeah?
Could there be also three separate active sites?
Yeah, that's the thing. So following Zoe's question, I don't know if there are enzymes with more than one active site. Because of, yes.
So now we'll just assume there's only one.
Yes, because enzymes carry out one reaction, typically. Yes.
Would it be possible for like two different enzymes to like come together into a quaternary structure and then form two different functions with like both of the active sites?
Oh, okay, that's an interesting question. Okay, I don't know if this is considered, let me think. I think that is possible. I think it's possible that you have multiple proteins, enzymes coming together to form an enzyme, what we call an enzyme complex, like many, many enzymes together. They may therefore work together to carry out. But I cannot think of a good example at the moment. But I think there are examples like that. Wow. Okay, sorry. So I forgot what we're doing. What model do you think these students try to represent? Okay, who says lock and key? Okay, I have a few lock and keys here. Okay, Keller, why you say it's lock and key? Just looks like it. Sorry, the watermelon seed what? Or it doesn't change shape. Even in the induced fit model, the substrate does not change the shape. It's the enzyme that's supposed to change the shape. Yeah? Wait, what? The watermelon seed what? Oh, okay. Oh, okay, to you, the shape has not changed. Okay. And so who else say is lock and key? Sion, why do you say it's lock and key? Or is it Yishuan? Oh, yeah, okay. Why do you say it's lock and key? Okay, no change in the shape. Okay. So bear in mind, when we look at induced fit model, it is not the substrate that changes shape. It is the enzyme that changes shape to fit the substrate. Okay. So to say that the substrate doesn't change shape, therefore it is lock and key, not quite accurate. Are you saying that the enzyme don't change shape? Correct, it is still the same substrate. So therefore it's lock and key? It won't become a smaller melon seed. Oh, okay. So to you, the cracker did not mold around the melon seed. Okay. Oh, okay. Sion, you want to say something? No? Okay. Oh, okay, how does this tool work? Maybe it doesn't quite make sense. This tool works like that. Your two fingers have to come in to press these two ends together. Then when it press in enough, right, actually this can go even more, this melon seed will crack. Okay, if you push this even more in, it will crack. Okay, so we've heard one that you think is lock and key. Who thinks the induced fit model? Okay, maybe we hear from Rin. Why do you think it's the induced fit model? Okay, so to Rin, the cracker changed its shape. To you, the cracker didn't change shape? Oh, okay, when the cracker moves, it is the reaction taking place. But for you, when the cracker moves, it is changing its shape to fit the active site. Okay, so maybe therefore we can clarify one thing. When the enzyme changes its shape to fit the substrate, the reaction is not happening there and then. Only after the active site has been formed, it forms the correct interactions and whatnot, then the reaction begins. Okay? Okay, so we could look at this from various points of view, right? The student many years ago got it to demonstrate to her. She feels like it's like an induced fit model. But at the same time, a lot of her classmates raised their hand and said no. For example, one of the things that the class said was that in an induced fit model, it's not like there's an external force that will come in to help to change the shape of the enzyme. But here you need fingers to come in and do it. That's one of the things that the class brought up many years ago. Okay, but to some students, this looks like a lock and key because the melon seed kind of fits quite nicely into the active site, which is this region over here. Okay, so I think this example was used just to spark a little bit of a conversation on what we think this model is trying to represent and its limitations. It's definitely not a very good representation of either. Okay, I think we're almost running out of time. Okay, so I think we will start to wrap up for today. Next week when I see you, I'll always see you for 3 periods first, right? Okay, so in that 3 periods, I'll see you in the lab. In the lab, we're going to make use of our favorite enzyme, amylase. Okay, we're going to use amylase to digest aminopectin or starch. And we are going to play with different temperatures. Because we learned that at very high temperatures, we could denature a protein, right? Would that happen for enzymes too? So that's what we're going to do next week. We're going to modify temperatures, and we're going to test the amylase functioning at various temperatures. May I get you to complete question 5 and question 6? You should be able to do 5 and 6 Okay, if you complete your SLS. Okay, if you should be able to do 5 and 6 if you complete your SLS. It's not sufficient, you also can read your notes. And I'll go through 5 and 6 next Friday. Question 7 and 8, again they are dessert and coffee. If you feel like going a little bit further to find out real examples of enzymes that fit this particular model. Okay? Actually, I really cannot find that many enzymes that fit this lock and key model. But you often find at a very usually when we will teach students this particular model first, because it's easier to see and understand. Yeah? It's often the very first touch point when students learn about enzymes. Just visually, it makes sense. Okay, so please go home, complete 5 and 6, or if you're willing, you can even work on it now if you already know what it may look like. Okay, then once you're done, you can go for a short toilet break. It's a rather humid day.